In this presentation, we'll talk about, still continue to talk about resonance, series resonance circuit in AC. And specifically, we'll talk about how you can calculate the bandwidth for a particular circuit. So what we would like to have is something called a sensitivity curve for power responses. And so we know that when we have our circuit set up with at resonance, so that the frequency is at the resonance frequency, that we get the maximum power in the circuit, right? Because all of the impedance in the circuit is resistive, we get the maximum current, and therefore we get the maximum power. So what we'd like to do is we'd like to have what these things are called, these sensitivity curves, which is basically allowing us to figure out what range of frequencies will our circuit respond to. And so we'll set this up so that our circuit will respond to frequencies in a range where the power is a maximum, and then also all the way down to half of the maximum power. And of course, because of the way this is set up, it would be we would have this range, right? We'd have a low frequency and we would have a high frequency where the power is half of the maximum. And we talked earlier about the fact that this range of frequencies is called the bandwidth. So it's the difference between those two half maximum powers. And those frequencies are called the half power frequencies, the lower frequency and the upper frequency. And so the idea would be that if we had some source and our circuit was responding to that particular source, that it would cut off anything below half of that power. So we'd like to be able to figure out, how do we figure out what the bandwidth is for our given circuit? And what does the bandwidth depend on? Is it going to be a large bandwidth? Is it going to be a smaller bandwidth? And so on. So a circuit that has a very narrow bandwidth has a high sensitivity. So that means that you'd have to tune things almost exactly to the right frequency, and we would get a high power output for that. If the bandwidth is wider, it has a lower sensitivity. So there's more flexibility in there as terms of your adjustments, but also you have a reduction in terms of in the power that you have. These cutoff frequencies, which are the half power frequencies, can be found by basically looking at the power dissipated by the circuit when it's at half of its maximum power. So our goal here is to try to figure out what these cutoff frequencies are, and then we can use that to figure out what the bandwidth is, because the bandwidth is just the difference between those two frequency ranges. So we're going to go through this step by step. It's not something you would have to necessarily derive on your own. So once we find the final answers, we can use those results, but it's good to know where that comes from. So our goal is to figure out at what frequency is the power equal to half of the maximum power. So in general, power is current squared times resistance. This is, of course, the real power. And the maximum power is when I have the maximum current in the circuit. In general, the current in the circuit is just the voltage that's connected to the circuit divided by the impedance. So I probably should have a picture here, but this power here at the half of the maximum power, this is a situation where in the circuit you have an inductor, you have a capacitor, and you have a resistor connected to a voltage supply. And so the total current in this circuit here is just the voltage over the total impedance. And these are not phasors, because power is not a phasor. These are just maximum values. On the other hand, when I have the maximum power and when the current is a maximum, that's when the inductor and the capacitor in the circuit, those reactive components, are canceling each other out, and all of the impedance in the circuit is just resistive. But in both of these cases, those voltages are the same because you're connected to some voltage supply. The thing that makes the currents different, of course, is the impedance in the circuit. So the voltages cancel each other out, and I can square both of these terms, and I can do a little cross multiplying, right? So I squared the r and brought the 2 and moved that over, and then the z squared and move it over to this side, right? So the v squareds cancel, and I get this expression that says that in order for the power to be half of the maximum power, the impedance in the circuit squared has to be twice the resistance in the circuit squared. So I can go ahead and I can plug in what the impedance value is for my circuit. So going back to previous presentations, I know that in general, I can write down the impedance in the circuit as the square root of the resistance squared plus the, essentially this is the reactive components squared. And then since the impedance here is a squared value, I have gone ahead and gotten rid of the square root. So this term in here is just the reactive components where we've put it over a common denominator, and then we've taken the rectangular form and we have written it in terms of the magnitude of the impedance. So you can go back and you can look at a previous part of this resonance video presentation, and you'll see where this expression comes from if you need to go back and look at that. So now I can move this resistance squared to the other side, right? And I have a term on the left side that's squared and a term on the right side that's squared. I can take the square root of both sides, but when I take the square root of both sides, I have to make sure that I put a plus minus in at least on one side. I don't have to do it on both sides because essentially that takes care of both situations in terms of taking the square root. I can now multiply both sides by the angular frequency times the capacitance, and I move that up over here. I still have the plus minus, and then I can move everything onto one side of the equation, and I have 0 is equal to the angular frequency squared times the inductance and the capacitance. When I move this term to the other side, the plus minus changes to minus plus, and I have this nice expression here. Now my goal is to figure out those half power frequencies. So my goal is to figure out what are these values for the angular frequency in terms of my circuit that has an inductor, a capacitor, and a resistor. So I have something where I'm going to need to use not Pythagorean's theorem, that is not what I wanted to say. The quadratic formula wouldn't come to my head right at the moment, right? So my unknown quantity that I'm looking for is the angular frequency. It has a squared component, it has a linear component, and then it has a constant. So this looks like 0 is equal to a, like x squared plus bx plus c, right? But instead of x, we have this angular frequency squared. So in my expression, my A value is L times C, my B value is minus plus RC here, and then my C value is minus 1. So I can continue and I can solve for the angular frequency using the quadratic formula. The quadratic formula says that the angular frequency would be minus B plus or minus the square root of B squared minus 4AC over 2A. I can plug all those values in that I have for A, B, and C. When I have them in this form right here, what I've done at the top, of course I have my B is minus plus, and then when I multiply by a minus it becomes plus minus. And the bottom is 2LC. I have just factored that out in this next piece up here. And I've also moved it under the square root here by squaring those components. And then I can write it in this fashion where I have the C's cancel out in the first term, so I have R over 2L. And then if I divide here, the C squareds cancel, so I have R squared over 4L squared. And then here the 4's cancel, and an L and a C cancels, and I get 1 over LC. Now the angular frequency has to be a positive value. Frequencies are positive, they're never negative. And so although there are actually 4 answers that I can get here, because I have a plus minus that I can change here and a plus minus that I can change here. So I could have plus plus, minus minus, plus minus, minus plus, right? So there's 4 answers. Only 2 of those answers are actually positive. So the term under the square root here is always larger than the term that's out front, because the term here, R over r squared over 4l squared is basically this term squared, and then I'm adding something to it. So the square root term is always bigger than the term out front, which means that the sign for the square root term has to always be positive. So that reduces it down to two possible answers. The term that's out front here, which is not part of the square root, can be negative, and that will give me the lower frequency. And it can also be positive, which would give me the upper frequency. So these frequencies are the half power frequencies. If I plug those particular frequencies in, they will tell me when the power is at half of its maximum for a given circuit. The bandwidth is just the difference between those half power frequencies. And so I can just take the difference between those two quantities that I found. And I notice that the square root terms are in both of them, and they are going to cancel. And then the term that's out front has a negative, but then I'm subtracting. So the bandwidth of my circuit is just the resistance divided by the inductance. And so if I have a particular circuit, I can figure out the bandwidth by knowing the resistance in the circuit and the inductance in the circuit. The units for the bandwidth here are in radians per second because my angular frequency is in radians per second. Sometimes I might want to actually know what the frequency is in terms of hertz. And so the frequency is the angular frequency over 2 pi. So I can take that answer and I can divide it by 2 pi. So the bandwidth with frequencies would just be the difference in the frequencies, and I could divide that number here by 2 pi and I would get my answer in hertz. So I now have a way of measuring what the resonance frequency is, and also what the bandwidth would be, as well as those cutoff half power frequencies that would then limit our circuit so that only I would have a certain range of frequencies that would be picked up by my circuit. It turns out that we can also write the bandwidth in terms of the quality factor. So if I multiply the top and the bottom of the expression for the bandwidth by the resonance frequency, then I can use the fact that the quality factor is the resonance frequency times the inductance over the resistance, which is basically this term here. All right, I'm kind of highlight with my pointer here. That term there is 1 over the quality factor. So the bandwidth can also be written as the resonance frequency over the quality factor, and that would be again in radians per second. So we can also talk about the bandwidth in terms of the sensitivity curves. And so in this particular sensitivity curve, we have the power, and our resonance frequency is constant, and also the resistance in our circuit is constant. And so we have also a set of, we have a capacitor and an inductor in the circuit. And what this sensitivity curve is showing is it's telling us something about the bandwidth. Is the bandwidth narrow, or is it more broad for each of these cases? And they're written in terms of the ratio of the inductance to the capacitance. This is a little bit tricky to understand what's going on, so we need to sort of talk our way through it. So bandwidth is defined as, we calculate it as the resistance over the inductance, and we know that the resonance frequency can be found as 1 over the square root of the inductance times the capacitance. And in this particular picture, we're saying that that resonance frequency is constant. What that means is that the inductance times the capacitance, which is how we figure out what the resistance or what the resonance frequency is, if that's constant, then those two quantities multiplied together also have to be constant, which means in my picture here, if I have an inductor and a capacitor in a circuit, in circuit 1, if I multiply those quantities together, it has to be the same as the multiplication of two other components together, or a third one. So in my circuit, I have these adjustable inductors and capacitors, and in my first circuit I have the two quantities here, and then in my second circuit I have another set and a third set. But regardless of which one of these circuits I look at, they all have the same resonance frequency, so those quantities have to be constant. What that tells me is that the inductance and the capacitance are inversely proportional to one another in the circuit. So if I increase the capacitance, I decrease the inductance, and vice versa. So if I go back to my expression that defines what the resonance frequency is, I can solve for the inductance. I can square both sides of the equation, and I can move the inductance around. And so I get that the inductance is equivalent to 1 over the resonance frequency squared times the capacitance. I can cross multiply, and I can write the 1 over the inductance is the angular frequency times the capacitance, angular frequency squared times the capacitance. If I substitute this into the bandwidth, I can write my bandwidth as the resistance times the capacitance times the angular frequency squared for this resonance circuit. Now, in this case, my resonance frequency and my resistance are kept constant. So resistance is constant and frequency is constant. So the bandwidth is only being affected by the capacitance in the circuit. So for a larger capacitance value, I will have a larger bandwidth, and for a smaller capacitance value, I'll have a smaller capacitance. So why didn't I just put up here, you know, large capacitance, small capacitance, and so on, and why is it in terms of this ratio? So what we have to realize is that the capacitance and the inductance are inversely proportional to one another. So if I have a large capacitance, that means I have a small inductance, and vice versa. If I have a small capacitance, I must have a large inductance. So what does that mean in terms of these ratios? So this particular example where I have the ratio of inductor 3 to capacitor 3 is larger than the ratio of inductor 1 to capacitor 1, this implies that capacitor 3 is small, so this number on the bottom of this fraction is small, and in turn, because it's inversely proportional to the inductance is large. So compared to L1 and C1, that ratio, the ratio of the inductance 3 to C3 is a large value. But specifically what it means is that you have a small capacitance, and a small capacitance means you have a small bandwidth. So when the ratio of the inductance to the capacitance is a big value, it's bigger than the middle curve here, you have a very narrow bandwidth here because your capacitance value is very small, right? Small capacitance, small bandwidth. So that's this one right here. And then we have the middle of the road one, and then the other one has a larger bandwidth. And the reason that has a larger bandwidth is because the capacitance is larger, so C2 is large. And if C2 is large, that means that the inductance has to be small. So a small number over a large number, that number is small compared to that middle curve. And so I have this, this larger bandwidth. So one way, if we have a constant resistance in the circuit and a constant resonance frequency, we can change the bandwidth by changing the ratio of the inductance and the capacitance. Another way that we could change the bandwidth is if we kept the inductance and the capacitance in the circuit constant, and we just changed the resistance. So the bandwidth is the resistance over the inductance. So for larger resistance values, the bandwidth is larger, and for smaller resistance values, the bandwidth is smaller. But you'll notice in this circuit that even though we have the same resonance frequency, we don't have the same power. So you're going to get the largest power when you have the largest resistance. So here's the larger resistance of the 3, right, up top here. A lot of power, narrow bandwidth, versus a smaller resistance, smaller power, broader bandwidth. So, you know, it's a matter of what you're looking for and finding that sort of that happy medium of what you want in terms of your circuit. Do you want to have a large bandwidth? If you want a larger bandwidth, you lose some power in the process. If you want something that's very sensitive, then you're going to have more power.